Good morning to all of you. This is lecture number 16. In this lecture, we will discuss about the numerical problem which is based on lumped analysis or unsteady state heat transfer analysis. This is a problem. A long pipe of 0.6 meter outside diameter is buried in earth with axis at the depth of 1.8 meter. The surface temperature of the pipe and the earth are 95 degrees centigrade and 20 degrees centigrade respectively. Calculate the heat loss from the pipe per unit length, and the conductivity of the earth is 0.51 watt per meter Kelvin. So in this problem, a long pipe which is 1.8 meter in depth from the earth, and we have to calculate the heat loss per unit length. So length is equal to 1 meter. The temperatures of the surface of the pipe and the earth are 95 degrees centigrade and 25 degrees centigrade. So we have to calculate the heat loss. So given data, the diameter of the pipe is equal to 0.6 meter, that is radius is equal to 0.6 divided by 2 is equal to 0.3 meter. Length is equal to 1 meter. Temperature of the pipe 95 degrees centigrade. Temperature of the earth 25 degrees centigrade. Depth is equal to 1.8 meter and K is equal to 0.51 watt per meter Kelvin. So in this problem, heat loss from the pipe, that is Q by L. So we know that the heat loss is equal to Q by L divided by K multiplied by S Tp minus Te, where S is equal to surface factor, K is equal to the conductivity of the material. The S is equal to the shape factor is equal to 2 pi L divided by ln 2D divided by R is equal to 2 pi multiplied by N. So L is equal to 1 meter and T is equal to 1.8, R is equal to 0.3. Putting all these value in the shape factor formula, so we get S is equal to 2.528 meter. So putting the values of S, K, Tp, Te in the final expression of the heat transfer, that is Q by L, is equal to 0.51 multiplied by 2.528 multiplied by 95 minus 25 whole divided, that is the final answer is 90.25 watt per meter, which is related to the heat transfer through a composite cylinder. A steam pipe of 10 cm inner diameter and 11 cm OD outer diameter is covered with an insulating substance of K is equal to 1 watt per meter Kelvin, and the steam temperature is 200 degrees centigrade and the ambient temperature is 20 degrees centigrade. If the conductive heat transfer coefficient between the insulating material and the air is 8 watt per meter Kelvin, find the critical radius of insulation for this value of Rc. Calculate the heat loss per meter of pipe and the outer surface temperature, and assume there is no resistance of the pipe material. So in this problem, there are two diameter, inner diameter and outer diameter, that is 10 centimeter and 11 centimeter. So the inner radius is inner diameter whole divided by 2, that is 10 by 2 divided is equal to 5 centimeter or 0.05 meter. The outer diameter, that is R naught, is equal to OD divided by 2 is equal to 11 by 2, 5.5 centimeter or 0.55 meter. K is equal to 1 watt per meter Kelvin. Ti is equal to 200 degrees centigrade and T infinite, that is surrounding ambient temperature, is 20 degrees centigrade. The heat transfer coefficient, that is H naught, is equal to 8 watt per meter square Kelvin. In this problem, we have to calculate the critical radius of cylinder, that is Rc. If Rc is equal to R naught, then what is the value of Q by L and the outer surface temperature? So we know that the critical radius of insulation in case of cylinder is equal to K by H naught, but in case of sphere, the critical radius of insulation, that is 2K by H naught, where K is equal to conductivity of the material. So K is equal to 1 and H naught is equal to 8. Putting this value, we get as R naught is equal to 0.125 meters. So this is the first answer. Critical radius, that is R naught, is equal to 0.125 meter. The heat loss is equal to 2 pi divided by temperature difference and whole divided by the summation of thermal resistance. Putting all these value, Q by L is equal to 621 watt per meter, because delta T is equal to 200 minus 20, and the first resistance of the material, that is Ln divided by Ln multiplied by 0.125 divided by 0.0504 divided by 1, plus convective resistance, that is 1 divided by 8 multiplied by 0.0125. So there are two resistance. The first resistance is conduction resistance in case of cylinder, and the second resistance is a convective resistance. Convective resistance is due to the convection mechanism, and the conductive resistance is due to the conduction mechanism. So the final answer of the heat transfer, that is Q by L, is equal to 621 watt per meter. So the next question is T naught, that is Q by L is equal to T naught minus T infinite whole divided by the resistance. So T naught, solve this equation. T naught is equal to T infinite plus Q by L multiplied by the conductive resistance. So T naught is equal, T infinite is equal to 20, and we have been calculate the Q by L, that is 621 multiplied by 1 divided by 8 multiplied by 2 pi 0.0125. So the final answer of the T naught is equal to 1018.72 degrees centigrade. The temperature at the inner and outer surface of the boiler wall made of 20 mm thick steel and covered with an insulating material of 5 cm thickness are 300 degrees centigrade and 50 degrees centigrade respectively. If the thermal conductivity of the steel and insulating material are 58 watt per meter degree centigrade and 0.116 watt per meter degree centigrade respectively, calculate the heat loss through the boiler wall. So this problem is based on a composite wall having a two layer of steel, and the first layer is steel and second layer is covered with the insulating materials. So the given values, L1 is equal to the length of the thickness of the steel wall 20 multiplied by 10 to the power minus 3 meter, conductivity of the steel wall 58, conductivity of the insulating material 0.116, temperatures is equal to 300 degrees centigrade and 50 degrees centigrade, higher temperature 300, lower temperature 50 degrees centigrade. In this problem, we know that the Fourier law of heat conduction through a composite wall, that is Q is equal to the delta T overall divided by the summation of total resistance, where RTL is equal to conductive thermal resistance of all the walls. In this case, there are two walls. First is steel and the second one is insulating material. So there are two resistance of conduction. So the first resistance, that is RTH1, is equal to L1 divided by K1 A1, and the second resistance, that is R2, is equal to L2 divided by K2 A2. So in this case, A1 is equal to A2 is equal to A, because it is a composite wall and the length of the wall is equal to 20 and 5 multiplied by 10 to the power minus 3. So putting all these value in this equation, we get the first resistance value, that is 3.45 multiplied by 10 to the power minus 4. This is the first answer, and the second resistance is L2 divided by K2 A, which is equal to 0.043 watt per meter degree centigrade. But we know that the Fourier law of heat conduction, that is Q is equal to the summation of the total resistance divided by the summation of the total thermal resistance, that is 300 minus 50 divided by the resistance of first plus the resistance of second. So putting all this value T1, T2, RTH1, RTH2, the final answer of the heat loss from this wall is equal to 5767.8 watt. In this lecture, we have to cover the two problems which is related to the heat transfer through conduction and the lumped analysis. In next lecture, we will discuss about the heat transfer through the composite sphere and the composite cylinder. Thank you.